All right. Hello and welcome to the short intro video on section 2.4. This is the section in your book on continuity. So we're going to go over real quick what continuity means, how to understand it, and some of the theorems associated with continuity, including the very important and very useful intermediate value theorem. So what does it mean for a function to be continuous at a point A? The idea is if we mark x equals a here on our x-axis and we draw the graph of some function, and we'll contrast this in just a minute with what it means to not be continuous, which is frankly a really good way to understand what it means to be continuous, is to realize what can go wrong. So the key thing here is that as we approach a from the right or left, so you can think of this as tracing your finger along the graph points as you get closer and closer to x equals a on the graph. So again, the idea here, I'll use the laser pointer, is that we look at values of x that are, say, approaching a from below, and we look at what happens up on the graph. So we can see this portion would be highlighted. We look at approaching a from the right, and we would again look at what's happening on the graph. And then we look at what happens at precisely x equals a itself. We get that middle dot. The key thing here is that all three of those numbers are the same. So explicitly, let me record this off to the side here. We say that f of x is continuous at x equals a if all three numbers exist and are equal. Okay, and what three numbers were those? Well, again, we wanted to understand how did the function behave as we approach from below, how did the function behave as we approach from above, and what happened right at the function value at x equals a. So we need these three numbers to all exist and be equal. The limit as x approaches a from below of f of x, the limit as x approaches a from above at f of x, and f of a. You're going to have outcomes associated to continuity. And the key thing is we're going to ask you to verify whether a function is continuous at a point. And I promise you, what we want to see every time is that you compute each of these three numbers and you show us that they're equal. That's a perfect answer. And frankly, anything less than that is probably not going to get credit. So you need to compute the limit as you approach from below, the limit as you approach from above, and the function value itself. And you need to show us that all three of those are equal. On this example here off to the left, they are equal, right? So here we come in from below. We look at how the y values are behaving. They do seem to be tending to where that yellow dot is. We look at the function value from above. We trace along the graph. Let me make that a little better so it's clear it's going along the graph. We trace along the graph. We look at how the y values are behaving. They do seem to be tending to the same y value that that yellow dot is at. And then we look at the function value precisely at a. So the limit, remember from sections 2.2 and 2.3, could exist even if the function value was not defined there. But the function is not continuous there. You need all three of these to exist. So again, as I said, continuous. So what do some discontinuities look like? My video might have gotten a little staticky there. All I was saying is to understand what, to best understand what it means for a function to be continuous, let's understand a little bit about what it means for it to be discontinuous. So these are not the only ways that a function can fail to be continuous. They are really good ways to keep in mind. So let's draw a couple examples. So we could have a situation where the graph was perfectly behaved. Oh no, this isn't going to work. Oh, wait, hold on. This is going to work. But partial. But there's a hole right at the point where the graph would, where the x equals a would be. So let me mark it again. So here's x equals a, and you notice the graph has a hole. So that's critical for this type of example. This is called a removable discontinuity. It's called removable because you could just fill in the dot and everything would be fine. The key thing, again, you got to understand, to be continuous means all three of these numbers exist and are equal. And in this case, f of a does not exist. So what's going wrong here is that f of a does not exist. If it doesn't exist, it can't equal the other things. Okay, here's a second situation that we could have. So again, we're going to draw a similar graph, except now we're going to have a situation where the graph has a jump. And that is indeed exactly what this type of graph is, or this type of discontinuity is called. This is called a jump discontinuity. It's called that because the graph jumps. And what you'll notice here is that as we approach, so again, to be clear, here's x equals a. And what you'll notice is that as we approach values from below, the graph is behaving like this. And as we approach values from above, the graph is behaving like this. So what that means is that as we trace our finger along the graph for values less than x or values greater than x respectively, we're approaching two very different y values. So what's going on here is that limit as x approaches a minus f of x is not the same as limit as x approaches a plus f of x. It might be, and indeed the way I've drawn it, it is the case that one of these, the function value actually does agree with one of those limits. That's okay. It doesn't matter. The key was, again, for continuity, all three of these numbers had to be equal, had to exist and be equal. So in the removable discontinuity case, it doesn't exist. And in the jump discontinuity case, they're not equal. Again, that's why the graph looks like it has a jump, because as you approach x values, or values of x for as you approach a from below, there we go, your graph is behaving one way, the y values are approaching one value. As you approach a from above, your graph is behaving a different way and the values are approaching a different y value. So that jump is precisely encoded by the fact that these one-sided limits are not equal. And then the final way that we can have this, again, I say final, there are other ways, but these are the ones that are sufficient for us to keep in mind. Will give you a really good understanding of what the heck's going on. We could have a graph that did something like this. And what's going on here, of course, is it's sort of a super special case of a jump discontinuity. The implicit statement here is that this function is in fact flying off to infinity. So what we're saying here is that we have a vertical asymptote. We're going to spend a lot of time with vertical asymptotes, but you've already seen this definition in section 2.3, 2.2. But we're going to spend some time with vertical asymptotes when we talk about drawing the graph. This is what we're going to call and actually I'm going to pause the video. No, I'm not going to pause the video. What do they call it? Types of discontinuities. This is called an infinite discontinuity. There are a lot of phrases for this. Frankly, vertical asymptote would have been a better phrase, but whatever. This is called an infinite discontinuity. I don't like the way that looks. And in this case, we see that limit as x approaches a minus of f of x does not exist. Again, we needed all three of those numbers to separately exist and equal. So I do think that keeping these three situations in mind is a wonderful way to remind yourself of what the definition is. When you're asked to prove that something is continuous, or you're asked to show that it's discontinuous, the whole thing is going to boil down to compute these three numbers and show whether or not they're equal. Then they all have to exist, they all have to equal. I'm going to highlight that. They all have to exist and they have to be equal. That's key. So these discontinuities, these example discontinuities, highlight some of the way in which that fails to happen. Right here, the hole means that that value does not exist. Again, you could fill in the hole, then everything would be fine. So that's why we call it a removable discontinuity. Jump discontinuity, we have this jump going on. And that's because the y values as you approach from below aren't looking like the y values as you approach from above. So your graph has a jump. And the infinite discontinuity is a really extreme case where, in this case, of course, the two limits existed. They just weren't equal, but this one, it doesn't even exist. So vertical asymptotes like this that we're going to study are, again, a great example of a discontinuity. Notice that x equals a is in the domain because I put a solid dot here. So that's okay. X equals a is in the domain, but that function simply doesn't have a left-sided limit at x equals a. And if that limit doesn't exist, then there's no way that it can equal the other values. the big theorem in this section, and there's one really big theorem. Well, I guess there's two sort of theorems. One is every function, basically, that you know is continuous on its domain. That's not quite true, but every function that you've ever really spent any time with is continuous on its domain. Polynomials are continuous on their domain. Exponential is continuous on its domain. Log is continuous on its domain. That's important, by the way. It is continuous on its domain. It would have a problem at 0, but 0 is not part of the domain of log. Cosine, sine, again, you have to be careful, but like things like tangent are continuous on their domain because the points where they have problems aren't part of the domain. So you do have to be really careful. When we talk about a function being continuous, you can have a discontinuity at a point of the domain. Notice x equals a here is in the domain, but the function is not continuous there. But you can have a situation, say like 1 over x. Let's draw it real quick. So if you look at it, the graph of 1 over x, you get something that looks like this. Hold on. All right, sorry, coming back to this. So we're looking at the graph of y equals 1 over x. And the graph, of course, looks something like this. And it has a well-known discontinuity at x equals 0. But notice that x equals 0 isn't part of the domain because this function is not defined at x equals 0. So despite the fact that there's a problem at 0, this function is indeed continuous everywhere on its domain. But sort of parenthetically, we'll add x equals 0 is not in the domain. So we do have to be careful. If we ask you whether a function is continuous everywhere on its domain, then you really do need to think about where the problem cases are going to arise, whether or not the function was even defined there. I want to point out real quick, for quotients like this, there's a pretty obvious, so indeed for rational functions, it's a pretty obvious situation that can go wrong where the denominator is 0, the function is automatically discontinuous because it's not defined there. And remember, if the function value is not defined, then there's no way that it can equal the other numbers. So again, polynomials are continuous everywhere, exponential is continuous everywhere, log is continuous everywhere on its domain, cosine is continuous everywhere, sine is continuous everywhere, tangent, so again, now we're getting into fractions. Fractions generally of continuous functions are going to be continuous except where the denominator is equal to 0. So tangent undefined when x is equal to 0. Those are places where you could look for discontinuities. Again, you just have to be a little careful. We generally are interested in points in the domain where the function is discontinuous. So a lot of those points are not in the domain. In fact, in the case of tangent, in the case of 1 over x, they're not in the domain. So that means that these functions indeed are continuous everywhere on their domain. So just something to keep an eye out when you read the book. The big theorem of the section. So that was a useful theorem, but now the big theorem. So the big theorem of the section is, I keep forgetting I've changed the eraser. Hold on. There we go. The big theorem of the section is called the intermediate value theorem. Since I have your attention, let me just quickly tell you about it. So the intermediate value theorem actually is quite a literal theorem. It says that if you have a continuous function defined on an interval, closed interval, the way the book phrases it. So if, let's state the theorem. By the way, theorems are big results in math. Most math papers will put in a lot of effort, a lot of argument to build to a big theorem. So things like the fundamental theorem of calculus, fundamental theorem of arithmetic, the intermediate value theorem, the extreme value theorem, these are the big ideas that are worth paying attention to. So if f of x is continuous everywhere on an interval, a closed bounded interval AB, and let's say n is any number between f of a and f of b. I'm going to draw a picture in just a second to explain what the heck's going on. Then then there exists, how's the book phrase this? A number C, okay, could be more specific, that's fine. A number C in the interval AB, where f of C equals n. Okay, I understand that that is something of a sort of abstract theorem to take into consideration. So let's draw a picture. Let's see what the heck this was saying. So here's what this theorem was saying. Let's pick some values A and B. We'll take A here, we'll take B here. Let's draw the graph of a function. It does like something like this. So this function is continuous, no breaks in the graph. A good rule of thumb for continuity is you can draw the picture, you can draw the graph without lifting your pencil. Not a math definition, but a really good one to have in mind. So you can draw the graph without lifting your math pencil. Let's find on this graph where the graph hits A and B. And notice again that the F values are the Y values. So here is F of A, and here, up here, I guess I need to extend my, my axis a little bit. Here is F of B. All right. So what the theorem says, so just to be clear, let's zoom in here. This function, f of x, is continuous on the interval from A to B. In fact, it's continuous everywhere we've drawn it. We look at where the graph hits A and B. We find the y values associated to those two numbers. In this particular case, f of A is smaller than f of B, but it did not need to be that way. We could have, think of like flipping the graph. You would have a generally decreasing behavior. What this says is if you pick any number n, let's pick one. So here's a number n that lies between f of A and f of B, then the theorem guarantees us that if we draw this dotted line, that there is at least one place where it will intersect this graph. And that value here is what is referred to as C in the theorem. Now, I want to point out real quick that it could be that there are lots of potential places. So just as an example, if instead we had chosen something like this, and you do the graph, then there would be 3 potential points. Notice that this first one, you might want to do a circle here, but it's technically outside the interval. That's okay. It's not a huge issue. But notice there are 3 potential places where this value C could be. The point of the theorem is that it guarantees you that there is at least one. So they could have actually phrased this a little bit more precisely. But what a mathematician would say is that there exists at least one point, C, where the value equals. There could be a lot. In fact, if the graph is constant, there could be infinitely many. So it's a weird theorem, and you probably haven't really seen a theorem like this before, in that it promises you that something exists. So this word here is crucial. Something exists, but it does not tell you that there's only one. It doesn't tell you how many of them exist, and it doesn't tell you how to find it. It just says that if you have a continuous function, it can't cross from A, from f of A to f of B without hitting every value in between. So it's a little bit of a weird theorem, but implicitly we use this all the time. This is the idea that if you move around, we know that position is a continuous function. So what would be a counterexample to something like this? If you're an X-Men fan, Nightcrawler, potentially. I'm actually not sure if they ever explain how Nightcrawler's movement works, but Nightcrawler potentially could, teleport, and you'd have a jump discontinuity in his position graph. But the rest of us aren't that lucky. So our graph is a continuous function, and all this says is that if I, start at my house and I drive to school, then I had to pass everywhere in between along my path at least once. Again, I could drive somewhere, reverse, drive, reverse, drive, reverse, drive, reverse, and then to go to school, I would have passed the same point maybe like 5 times. Doesn't tell you that. So all it tells us is that there has to be at least one, and it does not tell us how to find it. But sometimes that's good enough. So you'll see some of this logic in some of the results that come forward. Like sometimes just knowing that something exists is good enough, then we can go look for it. There are methods to try and find these values. They're just not detailed in the book. So again, it's a little bit of an abstract theorem, but it's a really important theorem. If the temperature was freezing, this will be pertinent right now because I'm recording this on January 22nd in Boston. So if the temperature is freezing now, let's say it's, in fact, I think it's like 15 degrees outside, and it gets to 42 tomorrow, then there had to be at least some point during the time between now and then when the temperature was 36, right? Because 36 is between 15 degrees, which it is now, and 42, which it's going to be tomorrow. Now, could also be that the temperature got colder. So you might say, hey, was there a time when it was 6 degrees? Well, that might exist, but doesn't have to. So again, the theorem makes no promises. I've drawn a, in some sense, my graph is a bit poor because of the way I drew it. But if I fix it real quick, let's actually fix it where this low portion goes below f of a. So notice now that there's this portion here that's below f of a. If you picked a number in here, there would indeed be a value of c, but the theorem cannot guarantee you that such a number exists. So the theorem only makes guarantees about values between the two numbers that you know. Doesn't say anything about these numbers, even though there would be values where that function value or that y value was attained. But the theorem can't make that promise because it could have been that the continuous function just looked like that. If that red line were the graph, then there would be no values, no c values that attained these lower numbers. But notice that this graph, this red line, again, just the simplest case of a straight line, also can't jump. That's the point. The intermediate value theorem says that a continuous function has to assume every intermediate value between where it starts and where it stops. All right, that video is a little bit long. I appreciate you sticking with me. I look forward to seeing you in just a minute in the 2.4 worked example video.